Łagoda, and it is with cooperation with Silesian University, Professor Kwaśny and Pawlyta from Ireland. This compression fatigue cracking for 6060 aluminum alloy and it's bronze specimen as the cyclic bending with torsion. At the beginning, I will go to the experiment, and next topography will be analyzed by Professor Małecka. This material is 6060. We talked today 2 times about this aluminum alloy and bronze. It's completely other material. No steel, because about steel you know very much, maybe you may say, but other material is not so. So we have aluminium and bronze. We have photo of specimens, aluminium and bronze, but the aluminium alloys, it was used 2 kinds of aluminium alloys, the treatment T64 and T60. It's very important. We make a static curve for this aluminium. T64 is 1 and T6. T6 is 10 larger, but it's problem with plastic deformation when we produce, for example, windows or doors in trains, because it's only we obtain from factory as we thought area. So this is very important. Experiment was made in stands which are produced in our university. We did many experiments on this stand. It is bending with torsion and every combination of bending with torsion. Here we have mass rotating, and after that you may start of moment, because if you define force, this doesn't work, on the force drumming of 200 millimeters, from you will have moment. When you rotate this moment, we obtain a bending with torsion, depends on rotation of our equipment. The specimen is put upper, it is bending torsion. Every time we have here, we have here or here, we have normal stress from bending and shear stress from torsion. Other is nearly zero, so zero, but it's nearly zero. And on the next, we put Weller curve, exactly, passing curve exactly. On the first slide, we have pure bending, pure torsion. Torsion is half of bending, and here torsion is bending. It is nominal value, but for this aluminium, nominal value is nearly the same as elastoplastic, because in fatigue regime, this material works as elastic material. We see that it's pure bending and bending with torsion, this curve is nearly parallel. For torsion, a little less. Marta Kurek, in the second presentation, told that it's, sometimes it's the same, sometimes so. Here you see this a little less. It is for 6060 aluminium, T64 experiment. This for 6060 T6, also bending with torsion, you see it's nearly the same. In point of fatigue is the same. For torsion, a little less, as similar area. For bronze, it's a little other, because we have also curve for nominal value, bending with torsion 2 times, it's nearly the same. For torsion, less. But on this equation, we put also elastic model. For example, here, elastic is red. Elastoplastic was calculated by elastoplastic. We see this is less, because the bronze is material with big plasticity. The same is for every curve. Also, we put in the first bending, we put curve for uniaxial push-pull loading. So we see that we calculated from nominal to elastic plastic regime. For bending and uniaxial loading, it is very the same. You have 6 specimens, so it's difficult to say it's other. So it's results of fatigue experiments. You see how many specimens it was made in these three combinations for these three materials. So now it will be topographic fracture surface analysis for the same Professor Małecka expert.
Okay, so good afternoon. My name is Joanna Małecka, and I want to present the second part of our presentation. So the images structure, images structure we can obtain using the test scanning electron microscopy, operating at 20 kV, and the secondary electron detection was used to obtain our fracture. Okay, so on this slide we can see the cyclic fracture for aluminium on the left side after T60 for treatment, and at right side after T6 treatment for bending, torsion, and for the combination from bending and torsion. For T6 the same, bending, torsion, and combination bending with torsion. And now we can see the fracture for bronze by bending, torsion, and for the combination of bending and torsion. And what we can see, now is the fracture for aluminium. And in this case of aluminium, the cyclic imitation is easy to locate. For each case, for TC treatment and G6 treatment, and the cyclic zone is accompanied by numerous and deep cracks, which are also clearly visible in the cyclic zone. Now we can see the crack propagation. The observation, the fracture of the residual zone is plastic and tactile, indicating that the end point was excited locally, and the numerous voids indicated that they were very weak areas of the cross-section, and therefore a convenient place for the development of the residual zone. Okay, okay. Now we can see the fracture for T6 treatment, and is almost the same. What more, the cyclic zone. The cyclic zone shows characteristic delaminations. It's caused by cyclic rubbing on the fracture surface, and below them, however, the zone showing characteristic plastic fracture becomes visible. Okay, maybe next. Okay, and the observation of the fracture zone, but only for bending and combination bending with torsion, we can see the micro area with cyclic strength with different orientation. Okay. And now cyclic fracture for bronze. And the observation confirms the general known mechanics of fatigue failure occurring during cyclic torsion and bending. We can see the cyclic imitation cyclic zone in each case, and the residual zone, which occupies most of the surface. A major part of sample in the residual zone is plastic fracture of a very fine structure. Okay. And the cyclic propagation is characterized by rough surface and an irregular fall propagating in a random direction. However, the observation of the fading zone in this, each case, we can see the fading station. Okay. Okay, and the conclusion for the first for the aluminium. So the static strength is depending from treatment. For T6 treatment, the tensile strength is 264. For T64 is 131. And similarly, in the case of yield point, for the T6 treatment, it's 258, and for T16, for 118. What more? For small durability, the treatment significantly impacts the fatigue strength. For greater durability, treatment is practically irrelevant. Fatigue characteristic for individual load combination are practically parallel. What more about the fracture? For aluminum, fatigue cracking always has a plastic character. In the case of bending and for the combination of bending and torsion, we can see the area with fatigue style, but in the case of torsion, did not have a microscopic fatigue stration. For higher loads, fatigue zone can be easily distinguishable from the residual zone. And for bronze, incorporation of the plasticity results in a reduction of the determinant stresses by about 25% in relation to the nominal stresses. Observation of the morphology, we can see the crack initiation place. Fatigue zone is created always in the material. Obtained fracture appears similar. Okay. It's all. Thank you.